Good afternoon, everybody. I am super excited to talk to you about the work we've been doing over at Meta for the last year or so on building this framework for data-centric experimentation. The system is called Matrix. It's powered by Ray, and it has been used to power some of our AI model training, and excited to talk about it. My name is Ramya Raghavendra, and I drive our data effort at FAIR, the Fundamental AI Research Lab at Meta. For those of you that might not be familiar, this is the research lab in the AI org. We work on essentially powering the next generation of research models. And let me get a quick agenda of what we are going to cover today. I will start with just giving you a background and motivation on how this started, what has been our journey of data-centric research at FAIR at Meta. And our eng lead, Dong, who will talk about the system we've been building, Matrix, give some examples of how to use the API, some of the features that it covers, as well as some downstream model training that has been done to build some AI capabilities, such as multi-agent collaboration and reasoning and other such AI capabilities. So, to get started, with some background. So, as we all know, AI models have been demonstrating jaw-dropping capabilities over the last few years. But let's remember, these models are only as good as the data that they consume. Now, this figure here sort of summarizes the journey of AI training data over the last 5-ish years. And you can, if there's two things you want to remember from this talk, I'll summarize 2 key takeaways. First is that on the left side of the graph, you will see an exponential rise. This steep increase in AI capabilities has been accompanied by a corresponding increase in the size of the data that is being used to train these models. We started with millions of data points to billions to now trillions of data points that are going in to train these models. So the last few years have definitely been about scaling of the data that's going into training these models. So that's the first takeaway. The second, if you look at the right side of the graph, is sort of where we are at today. I think there is a general consensus that we are at a point where we have essentially hit a wall of how much value we can get out of this human-generated data that is being used to train the models. If we want to continue to scale the AI capabilities, we need to answer the question, where is the data going to come from to power these? You've heard of, we have AGI, we talk about superintelligence. Essentially, in a few years from now, we are talking about AI that is going to be as smart or smarter than a human being, while at the same time, the reality of us saying that we have consumed about all the content there is to consume. So this team essentially tries to answer the question of where is the data that is going to power these AI models going to come from. So with that, let me answer the question that I just asked. Obviously, the last few years have been about let's consume the data that is on the internet, that is publicly available, clean it, and use it to train our models. You're a lot familiar with Common Crawl and various such data sets that have come out of it. If you want to continue to use data that is not human-generated and isn't about to get over, we're talking about unlocking other new sources. So there's data that is behind paywalls and data that is available to purchase, which is still human-generated data. And for a company like Meta, we have an opportunity. There's about over 3 billion users on the products. We have the opportunity to use product data, which, within the constraints of what we are allowed to use. But finally, and the reason we are all here to discuss this topic is that of using AI models to generate data that can then be used to train other AI models, also known as synthetic data. The synthetic data has seen as the promised land in order to get us over this data wall, for the reason that you can actually generate large amounts of data that can be used for training purposes. So there was one estimate that said that just based on the interaction and usage of ChatGPT, there's enough data that is being generated in 1 year that is equivalent to the amount of data that can be extracted out of Common Crawl after cleaning and so forth. So that's a huge amount of data, and we need to unlock it. The other is that there are areas such as reasoning or agentic data sets where we simply do not have the data to use for training these large training models. So we need to think about other ways of generating this data. So that's sort of how we think about the scaling paradigm and how we are going to increase the data quantity. I would be remiss if I didn't mention that data quality is just about as important. We need to make sure that the data that is going into these models is of high quality based on whatever are the parameters used to define that for your purposes. You need to make sure that you are not feeding information that is actually hurting the model performance. And you need to make sure that you are able to extract more value out of less data in order to break this exponential scaling. So that's another thing you need to take into account as you're building your data experimentation. So I want to sort of put these pieces together and give you a picture of what it is to build an experimentation framework before we get a deep dive into Matrix itself. Roughly, the steps are find high-quality data, and we just talked about how that's going to come from. You might be using AI models to generate this high-quality data. These models might be LLMs, diffusion models. It could be gaming engines. This is not necessarily synthetic in the sense that AI is generating it, but maybe it's physics-based rendering. Or it could be the other sources that I just talked about, which is still in the realm of human-generated. You might need to do data augmentation in the sense that there are some signals missing in it and that are necessary to train your models. One easy to relate example is that you have a video, I need to add captions to it, or if it's in a different language, I need to translate it. So there's a lot of audio, there's a lot of augmentation you might need to add. And finally, data curation, which is increasing the data quality that is going into your models, or actually looking at the specialized set of data that is of relevance to your model training. And then you take this data set, you feed it into your training framework. Data loading can be static. It can be generated on the fly if it's an RL-based learning system. And then Matrix itself works with any training framework, so we're not making any assumptions on what training is going to be used. Finally, you need to run your ablations. You need to have evaluations and benchmarks, which you're able to test the model performance against and make sure that the data sets you're creating are actually improving your downstream model performance. And then you ship these either as a research output, a publication, an open source model, or it goes into training one of the production models. So this is what the system enables. And with that background, I just want to, before I hand it over to Dong for a deep dive, I want to mention that this is work done by a large team. And essentially, the goal of the team is to foster this kind of data-centric, data-first thinking that thinks about how can we think of data as a first-class citizen in order to build powerful models. And a lot of this work has gone into models and products that are coming out of Meta. With that, over to Dong.
Thanks, Ramya. My name is Dong. I'm one of the research engineers in FAIR Data Foundation team. So as Ramya said, I will go over Matrix and also explain some of the API examples that researchers can use, and then underlying features that services that supporting those APIs. For research, I will go over a couple of research use cases within FAIR that use Matrix. Matrix is a research infra. So in FAIR, researchers use cloud to run their research experiments, such as AWS, CoreWave, And then on top of those cloud, so there's a common layer called the Slurm, which is a common research infra to get resources, scheduling jobs. So similarly, Matrix is actually building on top of Slurm. On the Slurm cluster, it will start help researchers to start a recluster. The recluster is not hosted services. So researchers individually or as a team, they can start many different Matrix instances within the cluster. So for each of the instances, there will be a recluster using those resources. On top of the resources, we build online services to do, for example, language model inferences, containers to run software, and also doing video encoding for embeddings, and also proxy to external API models. So this is the reserve-based services. We're also running a lot of different use cases using repipeline, similar to previous talks. On top of those services, we offer easy-to-use API for researchers to use to supporting various different use cases. On the API side, so as I said, the cluster API allows researchers to start a recluster easily using one command or a simple Python API. So once you have we also added recently HTTP service so that users can just curl something to manage their cluster, so including adding workers. Major part of Matrix is for LLM inference. So similar to the recluster management, you can also, using one command, to deploy most open weight models from Hugging Face, both from the command line, also from Python. Once you have the instance running, so there will be a very simple to use API to run a lot of the inferences. We do a lot of optimizations on this layer to make sure that the inference is efficient, which I will cover later. Containers are also important, for example, for running arbitrary code, if you are doing code gen, for example. The similar interfaces, we also call this applications. The application type will be container. So you can also deploy thousands of containers within one command. Once you have containers, you can allocate a container and then running arbitrary Docker images on that container. And then once the container is up, you can run command on top of the instance. Jobs API is something higher level than the previous language model or the container services. So Jobs is basically more user-facing. User will submit a function with resource requirements. So the job manager will make sure it acquires the resources, runs the jobs, and return the status and the logs. One example is the checkpoint evaluation. So researchers will doing a lot of fine-tuning on the foundation models. For each fine-tuned checkpoint, a separate evaluation benchmark need to be run. So there are so many checkpoints and so many benchmarks, so it's very hard to manage manually. So using the Jobs API, you can submit multiple checkpoints. You can specify what benchmarks to run, how many instances to run concurrently. And then once you submit this, and then later you can check back, and then using the command to figure out the status of the benchmarks running. For example, here, we're just saying, okay, we are interested in GPQA diamond, and then we are running 24 instances to get a stable estimate. And then here are the 24 runs. So in this way, we abstract the management of the checkpoint and benchmarks out of the using Matrix to automate it. So these are the examples of APIs. So now I'll go over some of the services that are supporting those APIs. To deploy a recluster, so researchers can independently running many instances of the recluster on the same like Slurm cluster. So there are many instances that we need to make sure they don't conflict with each other, so the system will manage the port assignment, managing the temporary directory so that there's no conflict. We're also using Slurm checkpointing to make sure that you can recover if the resources got lost. but you can continuously adding things to your recluster so that you can grow the number of workers when you have more capacity. So the Grafana dashboard is very important for us for debugging and performance. Later we'll show some examples. So using the matrix is very easy to set it up as well. LLM inference is very important for one of the matrix inferences because we use language models to do a lot of the data generation. So when we look at the available other frameworks, including LLM and SageMaker, etc. So matrix has some advantages, such as it runs on Slurm, which is very familiar with for researchers. It can run VLM instead of just running as a proxy. It's supporting both HTTP and gRPC. And because it runs on top of reserve, it can do auto-scaling. So we also open sourced the framework in April. So all these are nice features as a research runs on open source stack. We did a lot of optimizations. Two of the more important ones. One is the load balancing. The other is gRPC. Because we also know the rate ahead network can be pretty congested. To load balancing across hundreds of model replicas, we built a local cache so that the client can directly hit the workers to do load balancing instead of going through the head. So all these are also using gRPC so that we can avoid some of the overhead in HTTP. So here is a brief comparison with another popular LLM inference system on Slurm. It's called LLM Swarm. So the feature is we both use the same VLM backend, but the LLM Swarm load balancing through an Nginx proxy. So when we scale the number of GPU nodes and also scale the number of replicas, so this single proxy becomes a bottleneck, so that we can see a matrix scales better with more model replicas. As I said, we use the rate dashboard for a lot of the performance tuning to look at the metrics to see where the bottleneck is. So this is one of the reserve dashboard where you can directly observe the number of QPSs to compare the benchmarks, whether they can fully utilize the GPUs. For custom metrics, our framework can publish metrics to the rate dashboard. So here is showing the pending tasks across the distributed systems, and you can see how many tasks are being queued. The same metric, but it's a different component where you can see there is a potential bottleneck of the system where the pending tasks actually spikes. So you can look at this to figure out, okay, maybe we should scale this component. With all these optimizations, we look at to maintain consistent high request to all the model backend because the GPUs are the bottleneck. We want to fully utilize them. As you can see here, we can maintain a pretty smooth 12K request for all the model replicas across a long time. Now move to containers. Containers become more and more important when researchers want to research on code gen, research want to using tools for agents. So using Matrix, we can deploy thousands of containers concurrently. One of the differences of containers with LLM is the containers are stateful. You want to request a container and then continuously running command on it. You don't want to be routed to a different container. For this, we built a custom infra where we have the reserve, we have a registry, we have the container actors. Those are the array actors. The main importance is the array actor will map the registry will map the ID to the actors, so that once you can check out acquired container by its ID, and then we use the ID to request, the request will make sure to end up in the same app instances. So here is some overview of are we also doing offline data curation. examples like offline inferences, media generation, using the physics engines, doing video embedding encodings, doing dedupings. Here's a simple diagram about we're doing a semantic task clustering, where we take the last layer of Llama 8B and then project it to a 30D dimension, and then using DB scan on a subset to build the clustering, and then apply the cluster to cluster the whole data set. So this is one of the pipelines we use for text diversification using embeddings. Matrix is built to supporting research. So here we have the one of the research is using multi-agent collaboration, where we using Matrix to generate a lot of the traces. Using these traces, you can study the persuasive, assertive, and whether the language models can agree to each other and can correct each other's mistakes. So we use Matrix to generate 4.5 million docs, and using a lot of GPU resources efficiently. The last use case is basically for natural reasoning. It's a 2.8 million reasoning data set released to Hugging Face earlier this year. It's not based on the benchmarks. Instead, it's directly looking at web docs, such as DCLMs, using prompting and to run Matrix efficiently to generate the reasoning questions and also the reasoning traces. So this has been shown to improve downstream fine-tuning models' reasoning capabilities. So more work in progress. We'll upgrade as Ray and Will going improves, release new versions. We will look at multimodality. We'll running multi-agent data synthesis for use cases like Sweetbench and Tall agents. So Matrix is open source. Feel free to check it out and also contribute. Thank you. Any quick questions? We are slightly out of time.
I have a question. You said that you are using sticky sessions for the user to route to the same board again. Does Ray supporting it out of box, or why you have to do it? It looks like common functionality.
Yes. So we try to do it similarly in language model, so using some tricks. But for the container ID, we want the flexibility so that we can manage it.
The use case of this will not scale in production, right? Is it only for research?
Yeah, it scales up to our scale. So we basically running containers, and then thousands of them is manageable in our case. So if you really wanted to go to remove the single registry, you can, of course, scale that as well.
What is the use case I was trying to understand?
For containers, so as I said, we do code generation. So once the language model generates arbitrary code, you want to validate the code, measuring the performance. If it's ML, you want to measure whether the model post-performance. All these need to run in a secure container, and then the container can have different components. Similarly, if we want to do agentic data generation, then you need an agentic environment, which will be very easy if you have a container. Cool, okay, yeah.
Consider running resources on Kubernetes, and if so, what do you see the trade-off of using Kubernetes versus Slurm for resources?
Yeah, very good question. I think fair like infra teams are exploring so different ways to run the resources, whether it's Slurm or Kubernetes. So it's always debating. When we talk to researchers, they are more familiar with Slurm. So currently, yeah, so that's why I'm still using Slurm. But as more different things shows up, it's possible we should look at different ones. Yeah. Oh, all right. Okay.
Doesn't Matrix abstract away the Slurm infrastructure underneath? Does the researcher need to know Slurm? Because I assume everything is done through APIs.
Yeah. So right now, the training side are mostly still using Slurm. we added some capabilities supporting running fine-tuning on Ray, but the large-scale foundation model are still using Slurm because they are very thin. There's a very little overhead. Cool. Thank you. Yeah, feel free to chat offline. Thank you.